Good evening. I'm Charles Schultz with Schultz Laboratories, and this is the Randomizer. And tonight's subject is going to be William Gilbert. You may not have heard of him. He was a famous scientist born in 1544 and lived till 1603. And he made a number of very important contributions, which are things that we simply accept as the way it is these days. But at the time, they were considered rather radical ideas, and he published a number of papers and was actually a physician to two members of royalty. He was a British scientist. We'll get started with him very shortly here. So I encourage everybody to go to schultzlaboratories.com or universesciencecenter.com. Go to our page, click through, sign up as a member, and get all the benefits of our growing library of technical videos and tutorials. Become a member of our classes, which we hold Monday nights at 9 p.m. Eastern Standard Time. And we're starting up our robotics course very shortly. More information will be posted possibly tonight on our site, so you can go and explore what we have in mind. And I hope that you'll also take advantage of the fact that if you are an educator and wish to share your skills, we can create a virtual classroom or teaching environment or gallery for you online, and you can use that to share what you know with people all around the world. And that will be a great thing to do. Take your Oculus, walk around in our galleries, and explore a little bit and have some fun with it. So let's get to the subject at hand, William Gilbert. So as I mentioned, he was born in 1544 and he lived until 1603. And one of the things that he discovered that really made his name was the fact that the Earth had a magnetic field, and that's why compasses pointed north. He did numerous experiments in electricity and in magnetism back before 1600. He had a paper that he had published in 1600, which he called On the Lodestone and Magnetic Bodies, and on the Great Magnet, the Earth. And so when he was doing his experimentation, he recognized the fact that north poles and south poles of magnets would attract each other, and if it was north to north or south to south, the poles would repel. He also did measurements that showed that the magnetic field between a north and south pole fell off with distance by the inverse square law. Now, the strength of a magnetic pole on its own follows the inverse cube law, and there's a reason for that, which we won't go into tonight. But the fact is, he was one of the first people to take actual physical measurements of the attractive forces and repulsive forces between the poles of magnets. So he was a consummate scientist, and he was also a well-known physician as well. In 1601, he became the physician to Queen Elizabeth I. And then when she died in 1603, he was also the assigned physician for King James I. A few months after that, of course, he died, and it was thought to have been from one of the plagues that was happening at the time. Nobody's really certain at this point. But let's get into some of the things that he worked on. He did numerous experiments with electrical charge and electrical attraction. He was also the very first person to use the term electrical attraction and electrical force, as well as magnetic pole. He recognized that every magnet was a dipole. It had two independent poles spread apart from the center. And he also did experiments where you break the magnet in half and you don't separate the poles, you end up with two more poles. So each magnet always has a north and a south pole. So his experimentation allowed us to get a better picture of some of the elements of our universe, how well the Earth functions generating a magnetic field, and how navigation in the day depended really on only three specific methods. And one was feature recognition, you know, your landmarks as you're moving around. The other was to navigate by celestial mechanisms, such as the positions of the stars. And the third was to use a compass to show you an absolute direction that you can use as a reference. Now, what's interesting about the compass is if you construct a compass properly and the needle is of great enough length, you can mark out a circle around it in a number of divisions, typically 360 degrees. And then you can take a heading by adjusting your ship's position so that the North Pole is aimed at a specific number, and that would be your heading. So your ship is turning, the magnetic needle of the compass stays oriented in the same direction, and you get a certain number of degrees as a heading. Now, you'll also notice a very interesting fact about a compass. Whenever you look at a map, there typically is a pointed thing in old maps that look like a four-pointed star before smaller points or some fanciful version of this. It's called a wind rose. The wind rose has the north at the top of every map. And that becomes a tradition because then, by using north as your guiding factor, your map always matches exactly where you're going. And this is important. You actually had a place where you would place a map on a ship in many cases, and it would have a plate of material over it, sometimes a sheet of glass, that keep the map from being destroyed by water, and it was near the compass. So as you steered your ship, the needle on the compass would change, and you could take a bearing on the map and know what you were headed towards. And bearings this way are actually not perfectly accurate, but close enough so that most navigation worked pretty well over long distances. Of course, one thing that wouldn't show up is if your compass needle is pointed in the one direction, you're traveling at an angle, but the ocean currents are moving sideways, then you will end up missing your mark. And so they would also drop a rope out of the back of a ship that had a number of knots tied on it, and they would measure how many knots, how quickly the knots would drop in the water. And this is where the nautical term moving at a speed of so many knots came from. And that's why it's spelled K-N-O-T, just like a knot in a rope. They measured your velocity by how rapidly the rope would play out when they had a flat board or a paddle at the end, and the movement of the ship would drag at a certain rate. So your speed was estimated in how many knots would be pulled out in a certain period of time. But this also gave you a second indicator. The direction that the rope was paying out would also show you sometimes if there was some side slip in your travel. Well, anyway, much of this depended on the work of Mr. Gilbert, and so being able to make a discovery of this magnitude and also to do some of the earliest experiments in electrostatic force and magnetic force, the strength and how it operates, places him squarely as one of the prime scientists who ever lived. And the reason for this is, consider, what instruments did they have in 1544? Not very much. Everything you had at the time had to be handmade. But one of the things that came out of his research, he agreed with Copernicus, who stated very clear things about the structure of the solar system, the movements of the planets. One of the things that he said was that the Earth spins on its axis. Now, people didn't really understand at the time. They thought that the Earth was fixed in the center of the universe in many places. And as you know, as advanced socially and technically as you think that they would be by then, they didn't really quite have it all figured out yet. They felt the Earth was stationary and everything went around it. And they also felt that the Earth was the center of the universe. Many people still felt that way. Well, it's pretty clear by his time that Copernicus was taking a slightly different view of things. He agreed with Copernicus. The Earth was in motion and rotating. And this was one of the things, think of it as a tipping point in thinking that showed that this planet itself was dynamic and moving and not necessarily stationary and locked down as a center of creation. And it takes a lot of courage to go against the word of the church, at least it certainly did back then. He also showed an interest in astronomy that went beyond simply looking at the sky. By taking observations at various times of the year and working through logically, he came to the conclusion that many of the stars were at different distances from the Earth. So this is a huge fundamental step forward, that the stars were actually not just dots of light on a shell, which was the prevailing view of the day, that there literally was a sphere around the universe that had dots of light on it. He felt that this shell model was incorrect and that the stars were independent entities giving off their own light at varying distances. Well, this is also a huge step forward. Astronomy benefits from the things that he learned, and he also had an interesting theory. Discovering that the Earth itself had a magnetic field carried a little more import in his mind than simply the act of navigating by a compass. He knew not what was creating the field, but simply that it was present. But he also gave that some thought in terms of the movements of the planets themselves. In the day, people didn't believe that there was simply a nothingness out there and everything falling through it. But it was becoming pretty apparent that something other than being painted on a sphere or attached to a wheel was making the planets follow their paths and not simply fly off into space. Gravitation was one of those subjects that was not addressed very fully in the day, and so they didn't have a great deal of information about it. Now, the experiments of Newton happened later in the 1600s, and so Newton's work was not yet done to define the force of gravitation. So many of the explorations and experiments that were done pointed in that direction, but they still didn't have definite proof at the time. So this is very important. One of the things he felt was that the planets were held in their orbits by some form of magnetism, which, if you consider it, was not an unreasonable thought. Of course, we know today that it's actually a gravitational field, but he had a step in the right direction. So when you consider how little people had to work with in terms of technology, you have to understand the ability to create and use electrical currents, the ability to experiment with magnetism, and the foresight to actually come up with working terms for these things are all fundamental principles and advances that the world had not yet seen. Now, we do know that Greeks in the past knew the shape, distance, and size of the moon from the earth, and they had measured that by the height of shadows at two different points on the globe. So at noon on a specific day, when the shadows of the sun were non-existent in Alexandria, because the sun was exactly directly overhead, at that time, a measurement in Athens showed a variation of 15 degrees. So this was used to calculate the angle of the ground at those two distant points. And indications were, from watching ships go over the horizon, obviously, that the planet had a curvature to it. They weren't sure if it was just like a tube or like a ball, but eventually they did resolve that. But by using the difference in the angles and knowing the distance from Athens to Alexandria, they were able to calculate the actual radius of the Earth. And they were within 10%. So the size of the Earth was known and calculated. And then during eclipses, seeing the shadow of the Earth on the moon gave them a measure of the size of the moon. So they were able to calculate the size of the moon very closely, within 10%. Then, because of the angle, the width of the moon, which is roughly half a degree, they were able to say, hey, we know the distance now. By simple geometry with a compass and straight edge, they were able to figure out the size and distance of the moon from the Earth. So now, following these trends and understanding that the moon was a free-floating body, was not attached by a cord but some other force, William Gilbert actually reasoned out that there were many things in the universe that were not attached to anything and seemed to be held by this mysterious force. So I can't stress enough how much of a leap of logic it took to put these pieces together and make these discoveries. And he's certainly one of the most interesting people that I've read about in historical times. So William Gilbert, an exceptionally bright man, a physician to a queen and a king in rapid succession, and in his later years, he passed away, leaving a couple of manuscripts behind that had not been published. And they were his works that he was completing, but never had the opportunity to. His works were edited by his brother after his death, and it took until 1651, 48 years after his death, to have them published. But once they were edited and translated, the title was A New Philosophy of Our Sublunary World. So he had already put together a philosophy of the Earth and how it worked and some of its properties. And by the way, sublunary is a term meaning of belonging to this world as opposed to a more spiritual or perfect world. So he recognized the flaws in our reality and worked from that concept. And again, as I have to stress, religion was a huge force in the day, and often you had to couch your terms in such a way as to not offend certain church members. Just the same, He certainly was a heroic figure in my mind because of the fact that he was able to derive so many interesting conclusions from some of the most basic principles and materials. I would say a lot of people that we know would not have the ability to create a battery and make electrical experiments worth anything. Um, it's one of those things that unless you really know the principles and you're familiar with how to get the materials together, you're not just going to just go out and do it. You don't know how. In his day, in the day of Dr. Gilbert here, he had to actually come up with the copper and the steel or the iron and the acid and the vessels and all the materials and create his instrumentation, which was not actually out of the realm of reality because a lot of scientists of the day did exactly that. With very crude materials, they were able to fashion a lot of the hardware that foresaged what became our world, the modern world, with electrical devices, motors, computing, optics. All of these things were figured out centuries ago, and most of the equipment that scientists of the day used had to be handmade by them. So, you don't see a lot of scientists out there building their own equipment these days. They often go and buy something and assemble something from that. So, my hat's off to him. Definitely an interesting figure. So, if anybody has any questions about William Gilbert, or the magnetic field, or other objects that we've discussed here, I couldn't tell you much about his manuscripts. I have not read them, but honestly, it's a fascinating study. The floor is open for questions. And again, I'm going to urge people, go to the Universe Science Center, go to schultzlaboratories.com, and sign up as a member. Become one of our little people who explores and shares with their friends and gets everybody interested and whip them up. And go to our library page, which I am posting now, that has a list of all of our randomizer episodes. You will be able to see an index very shortly that puts all of the episodes in alphabetical order so you can find the concepts that you want and watch that particular episode. Go in there, have a look at them, enjoy them. I have a lot of fun making them, and there are going to be many, many more very soon. You know what? I failed to put the name William Gilbert up on my screen. Sorry, I got so engaged in what I was talking about. William Gilbert. Okay, so anybody have any questions?
Yes, hi, Charles, this is Elizabeth.
Yes.
Yes, I was wondering about how he had understood the distance of magnetics and its effect. Did he understand the principle of the square cube law? I mean, was that actually something that he derived, that actual statement? I have another question too.
Okay, so actually it's not the square cube law in this case, it is the inverse square law. And what he would do is he would measure the pull between two magnets at varying distances. And so they did have scales, they did have balance scales, and they did have the ability with springs and weights to create measurement systems that could actually give you a reading. And so reading the distance and reading the pull, you plot your numbers and then you look for a relationship and you find that it's related to a square root. And so 1 over that square root or 1 over that square gives you the inverse square law. So actually, when you have a lot of time on your hands and not a lot of internet to look at, people do have the time to actually work mathematical rules out with pencil and paper. Okay, and your other question, whatever it may be.
Yes, my other question is, did he have a compass at the time? And he did figure out how to navigate to some extent. So how does that affect the longitude and latitude where they were looking for longitude specifically?
Okay, so that actually isn't part of the issue. What he did is he studied the properties of the compass, recognized that they were actually magnets, and realized in the day that it was called a lodestone, Lode, lodestone. Magnets in that time were only of natural provenance. There is a land called Magnesia where natural lodestone exists, and this is an iron oxide mineral that has been magnetized, and it could have been by a local strike of lightning or any of a number of forces. But these natural magnets were prized, and They would mine them and shape them, and they would put a small piece of it on the spinner of a compass, and that's what would aim the compass in the proper direction. And so natural lodestone was the magnet of the time. They did not yet understand the connection between electricity and magnetism. That was to come later with the Ørsted experiment. So he was not a person who navigated, but he knew that mariners did. And so he had plenty of information from people who traveled the world to work with, and also the fact that he had a compass that he could work with. And it's not hard to make a compass. Any of us can do it quite easily. So his contributions were basically both the mathematical rule that described the varying pull between the poles of the magnet and the fact that the Earth itself is a magnet. Okay, so anything else? Well, very good. I'm going to read my quote for the day. He who believes and is baptized will be saved, but he who does not believe will be condemned. And that's Mark 16:16. Well, what more is there to say? I hope that everybody has enjoyed this episode of the Randomizer, and we will have another one tomorrow. And this has been an interesting look at William Gilbert. I'm sure you can find a lot more material online, and I recommend it. Sometimes just reading about somebody's history can give you a little bit of the viewpoint of the things they had to face, the adversities, and how hard they were to get their conclusions. So everybody have a wonderful evening. Thank you for coming, and I hope that you will join us tomorrow at 6 p.m. Eastern Standard Time for the Randomizer. So everybody have a great evening. Thank you for showing up, and as usual, make the world a better place. Thank you.